Thank you all so much for joining my talk today. I'll be telling you about how we've been building trust in machine learning by mapping the model lifecycle for machine learning integrity and transparency. This is joint work with my colleague Marcin Spoczynski, who could not be here today. So let's get started. A little bit about myself before I move on. I'm a researcher at Intel Labs, where I lead software and machine learning supply chain security research. Through that, I'm also heavily involved in open source, where I'm a member of the TAC and the OpenSSF, as well as a maintainer for some core projects like InToto and SLSA, if you're familiar with those. I also co-chair the BEAR working group in OpenSSF. And in general, I'm interested in the security of distributed systems and data centers and operating systems, so I tend to bring that lens to the work that I do in the supply chain space. I'll start by talking about why machine learning lifecycle transparency is needed and cover some of the ongoing efforts to provide model integrity. Then I'll talk about Atlas, our open framework for end-to-end machine learning transparency. I'll cover some stakeholder needs and how we get there through data and supply chain provenance together with trusted hardware. Then I'll show a short demo before I wrap up. So anyone here who's worked with models, trained them, fine-tuned them, studied their supply chain, will find this life cycle I'm showing here pretty familiar. But just to level set with everyone here, a typical model life cycle starts with a data processing pipeline that takes in raw data from one or more data sources. And the data set that comes out of that is what's passed into the training pipeline. And typically, a foundation model is what comes out of that. And depending on whether you are operating in an enterprise setting or an open model setting, the model hub that you upload your foundation or any trained model to may be internal or external. But either way, the pre-trained models that are stored at these hubs are what go into a fine-tuning or evaluation pipeline. And so by the time that a user interacts with an inferencing pipeline, they're typically interacting with a fine-tuned model. But I'm heavily simplifying this. There are a lot of cycles between probably all of these different pipelines. These pipelines sometimes have hidden dependencies and processes. I'm not showing a lot of the system components that each pipeline sort of requires. And so this complexity actually just leads to a lot of supply chain risks. And so for data processing, for example, specifically, data poisoning is a threat that we've seen both in academic and industry publications, where training data is compromised through malicious samples or sort of malicious perturbations to the data. And these changes do propagate down the life cycle. For any machine learning as a service provider, that can be model training or any other pipeline, we've also observed a number of vulnerabilities, including system components, malicious insiders, that can again have an impact on the final model that is then used. Similarly, hub compromises have also been recorded, and so here the intent is to tamper with a model as it's being distributed by sort of uploading a malicious model, trying to get sort of downstream consumers to download a malicious model. So in general, any model that a pipeline ingests from a third party, especially if it's downloaded from a public model hub that has thousands of these, they typically have opaque origins. Kind of how they were created isn't really easily known, and that can lead to further risks. And so if any of these pipelines is outsourced in general, the pipeline specifications, configurations, the systems that they ran on are typically unknown right now. And across the entire lifecycle, if at any point any of the model artifacts are not authenticated, between these different stages, then sort of additional tampering can occur and go undetected. And so the reason we need machine learning lifecycle transparency is because all of these risks that I just talked about make it much more difficult to answer the question, can I trust this model? They're all part of this trust question, and so there are approaches to start providing integrity for models. Typically, we sort of group together software and machine learning supply chain regulations that demand provenance and transparency, because a lot of the sort of software cybersecurity regulations do also apply to machine learning. They're coming out of the US and the EU. I imagine several folks here are familiar with these, or at least have heard of them. And so to address these regulations, to facilitate adhering to them, we're starting to see a number of model integrity frameworks emerge. And so the way that model integrity is achieved today is through digital signatures. And so if we come back to this pipeline that I just showed, in addition to the sort of regular pipeline, model signing will sort of generate the produced model artifacts using a format called in toto. These are stored in a SIG-store log. I'll describe what those are in a minute, but the idea here is to allow model users or any sort of downstream consumers to validate the signatures and any other cryptographic proofs that are produced along the way. And so for folks who are not familiar with model signing, it's an emerging project coming out of the OpenSSF. I think V1 was just released recently. And the goal is to detect tampering of models after they've been published to a hub by digitally signing them. In toto is a framework for generating and verifying authenticated claims about any aspect of the software supply chain. And so model signing uses in toto to wrap the signed model artifacts in a common format that can convey any type of metadata and be understood by other supply chain tools. The SIG-store framework provides an identity management service, so developers don't need to manage cryptographic keys on their own, and a transparency log that tracks when in toto claims are signed and issued. So what we get from this is cryptographic integrity for trained models, and we can start answering questions like, was this stored model that I downloaded tampered with? The issue currently, though, is that model signing typically only covers sort of the artifacts in between these stages. And so there's kind of still a need for end-to-end provenance for the machine learning lifecycle across all of these different kind of supply chain stages. And so this is why we started to develop Atlas, our open framework for end-to-end model transparency. What this allows us to start doing is capture trust expectations more concretely and verifiably along the entire lifecycle. And when we started developing this framework, one of our goals was to make sure we could address real stakeholder needs that are not met today. And so the model producer wants to be able to know if their model was trained or fine-tuned on the expected data set, the expected machine learning frameworks, configuration, so they can have stronger assurances that the supply chain for their model was not compromised. Machine learning as a service providers who may be sort of internal services in an enterprise setting or a third-party external service, they want to be able to provide evidence that they ran a customer's pipeline in the expected way. For one, such evidence can facilitate debugging, but it can also help corroborate the service provider's proper configuration and behavior in the event of an issue. And so before I go on to describe Atlas more in depth, I want to be very clear about the things that Atlas does and does not provide. So when I talk about provenance, I'm referring to the information about the origin and history of transformations to a model artifact. And so again, model artifacts are data sets, any scripts used to run a pipeline, configuration files, and of course the model itself. When I talk about integrity, similarly, for these artifacts themselves and the provenance information, integrity means that they match the expectation, and transparency gives us the ability to cryptographically audit the integrity and provenance. What Atlas does not capture is information about things like model quality, safety, bias. We're really trying to set a solid foundation to enable those more complex verifications later. And so Atlas is built currently on two main building blocks. The first is C2PA, or that stands for Coalition for Content Provenance and Authenticity. This is a standard for tamper-evident metadata about digital content. So think images and videos. That's what it was originally designed for, to sort of validate the authenticity and integrity of these media files online. But the standard has been developing sort of extensions to the current specification to support model artifacts and data sets. And the second is Intel Trust Domain Extensions, or Intel TDX. That's a hardware-based virtual machine granular memory encryption feature and integrity checking feature on recent Intel server CPUs. TDX is also remotely attestable so that third parties can actually authenticate a particular virtual machine that they're interacting with. And so the main goal of Intel TDX in Atlas is to provide that hardware root of trust for the generated provenance information, and in some cases even the pipelines that are generating this provenance. And so together with these two building blocks, Atlas has a couple of different modules, essentially three main components. First, the provenance module is what's actually responsible for generating the cryptographic hashes of artifacts for their integrity, as well as monitoring pipelines at runtime. And all of this information is linked cryptographically through the C2PA manifest when that's generated. And for those who aren't familiar with C2PA manifests, if you know what an SBOM is, a manifest is very similar. It contains the ingredients of a particular model. But provenance is only useful if you can actually do something with it. And so the other, or I should say the second main component of Atlas is the verification module that actually verifies artifact integrity and model lineage. So that's the provenance across all of the stages of a life cycle. And these two modules are supported by the Trust Foundation, which handles pipeline attestation. It contains the transparency log and relies on the Intel TDX hardware integrity features. And so putting all of this together, for each pipeline that is run with Atlas, there's the provenance module that's running alongside it, and this is then also run inside of an Intel TDX VM to provide that trust foundation I just mentioned. And so then at runtime, when the pipeline is running its operations, the provenance module will monitor the inputs and the outputs and collect signed metadata about the input artifacts and what's coming out, and some additional information about the system, and that is then stored in a transparency log. At inferencing then, the Atlas verifier checks not only the integrity of individual artifacts, but the entire provenance chain that has been collected up to this point. And so then a model user, or really any stakeholder in this life cycle, can request model provenance verification results or individual pipeline attestations. Okay, so I think at this point it's time for a demo, so I'm going to exit out of here for a little bit. Oh, I actually forgot to show you this. Here's the demo setup that I'm going to show. For simplicity, I've simplified the system a little bit, but we're going to be running a training and evaluation pipeline. I'm going to be mocking those up so we don't spend a lot of time here. The other thing that is being mocked up today is the TDX virtual machine. We're running in a mock environment, again, just for simplicity of the setup here. And so assuming that these pipelines are running in sequence, each time the Atlas CLI tool will generate signed CTPA manifests for the individual artifacts. The TDX workload attestation library will obtain a hardware-based attestation, or again, in this case, a mock attestation. Once all of this information is collected, the CLI will link the different manifests and attestations and store them in a backend. I'm using MongoDB because we haven't completed our transparency log implementation. That is upcoming. And so anyway, now I can switch into the demo. And I'm running MongoDB over here. And so I'm just going to start running our script. And so this is a preliminary step to generate our provenance signing and verification keys. Ordinarily, a system like Sigstore may provide this for you. And so assuming that we're about to run a training pipeline for something like, on something like the MNIST training data, we're going to download that from Hugging Face and create a manifest for that. Our Atlas system will give us a unique ID for this manifest. And just to give everyone kind of a basic idea of what this looks like, excuse me, you can kind of see here where this data set came from, the sort of organization, the user on Hugging Face, and just some extra information. And so at this point then, if we assume that we've run the actual training pipeline, now we want to generate a manifest for the outputs and the scripts involved. And so we'll generate one for the training script and one for the actual model that was generated through this training pipeline. And so if you take a look at the model's manifest for a moment, we have some metadata about what it's called, when it was generated, and its unique ID. And so the most interesting part here for me is actually linking the different manifests together so that we actually have the inputs and the outputs cryptographically linked, and we can start to create this kind of longer provenance chain. And so we're going to link the training data set to the model, and you can see that our model ID has actually been updated. And if we link then the training script as well, it's again been updated. And so now the model's manifest has these edges here that actually represent the links between the different artifacts and between the pipeline. And we can see here the data set is in here now, right? The actual model is this classifier. Here's the trusted hardware piece. Again, this is mocked up, but you could imagine in a real TDX environment, we would get a number of cryptographic hashes about the virtual firmware and that sort of thing. And so this is essentially what a linked manifest looks like. And so we can do the same thing again for a model evaluation pipeline. We've generated manifests for all of these. We've linked them together. We have a bunch of different, again, artifacts that we're tracking. And so we export the entire provenance graph to a file. And the other very interesting piece at this point then is to actually validate the provenance. And so we can validate the trained model, and we can see that the verifier identifies two cross-references, and so those are the data set and the training script that we ran, and hash verification is successful. It seems like I did not update my system here to add the mock TDX attestation, so the structure verification is failing here, but you can hopefully see how this flow would work. And so similarly, if I validate the evaluation results, we find three cross-references because we have the model now, the training data set, or test data set rather, and the evaluation script. And again, my evaluation script, which supposedly ran instead of a TDX environment, that particular metadata is not recognized, but I need to update this. So I also want to quickly show what happens if we try to cross-check with a bad link. And so for a given, if the link is not actually found in there, the verification should fail, and it does. And so just to sort of wrap things up, here's the entire manifest from data set ingestion before training, for the training pipeline, and then for the evaluation pipeline as it comes after that. And if we were to pass this group of edges into some visualization tool, then we could hopefully see sort of a graph that is generated from that. And again, everything is in here from the beginning. So yeah, I think that sort of wraps up the demo. So going back in here. And so I think what we have is a very good starting point, but we have several next steps ahead of us. First, we really need to integrate with the 6-store and model setting projects. This will allow Atlas to be more interoperable with existing tools and frameworks. Of course, this also includes adding support for the in-toto attestation framework. And some of these efforts are already underway. Similarly, we want to implement the supply chain levels for software artifacts framework in Atlas, or SLSA. This framework, because it provides a set of requirements for integrity of different aspects of software supply chains, we think that these can be applied to machine learning pipelines as well. So we're currently looking at implementing the build and build environment tracks to collect additional provenance information of machine learning pipelines. And more forward-looking, we completely acknowledge that a lot of machine learning pipelines run on GPUs and other special accelerators, and so that is a bigger effort that we have ahead of us, as well as interoperating or integrating with sort of emerging model metadata specifications like model cards, and that will allow us to capture additional metadata again about the models that we're generating. All right, so if you take nothing else away from this talk though, end-to-end machine learning model lifecycle integrity is important because models are susceptible to a variety of supply chain risks throughout their lifecycle. What we're trying to accomplish with Atlas is establish a verifiable link between the model artifacts and the pipelines that create them. We accomplish this by using existing data and supply chain provenance standards together with cryptographic techniques and trusted hardware to enhance the transparency of model lineage end to end. And what we get out of that is now we're able to address two important model producer and machine learning as a service provider questions about the integrity of their supply chain. And so the Atlas CLI that I demoed today is available as open source, version v0.1. It is not ready for production, and so we're absolutely open to collaboration and PRs. Please reach out to us via email, or you can find us on Slack. We're pretty active on the OpenSSF Slack server and the COSI Slack server these days. So thank you so much for coming. please go ahead.
I was wondering how much time it takes to build this for an actual scale model, and someone wants to know how long the process is going to take to do this.
So when you say build, do you mean integrate something like Atlas into the pipeline, or do you mean generate all the metadata? We've not really evaluated this on really big models, right? We've done this on small LLMs. Generation is still, like the actual provenance generation is quite fast. The trickier part is integrating with particular actual, how should I say, pipeline workflows. So one thing that we've tested is running with Kubeflow, for example. I don't think it was a trivial task, but it also wasn't something that took us like months. So I guess on the order of that, that's probably the best I can give you right now. But yeah, hopefully that answers your question. Go ahead.
Are there any enhanced security risks of downloading a model weights from other places?
Yes. So if these weights are not authenticated, so if they're not signed, if you don't understand their origins, and you're just ingesting them without any sort of validation, at least knowing the party that published them, if you can establish some level of trust in them, you can start to have stronger assurances or confidence about their trustworthiness. But if they're just, yeah.
What risk could the weights actually bring themselves over the value?
So the focus of this work is about the integrity. And so changing the weights will probably change how the model behaves, right? We're not capturing that in Atlas though, right? So as I said before, we're not covering any sort of model quality properties, but even understanding whether weights have been tampered with or modified in an unexpected way can give you, again, extra assurances that they're actually trustworthy. So, yeah. Andrew.
How do you think that CTPA and false provenance, comparing CTPA and false provenance, how are they the same, are they different? Because I know when we talked about AI models and false before,
yeah.
We said essentially that there's nothing inherently different in the model supply chain, why it wouldn't be represented as a problem?
Yeah, that's a question I get a lot, actually. I think we went with CTPA because we wanted to sort of start with like a data provenance angle, whereas I think CTPA can complement SLSA because SLSA focuses a lot more on the actual process and capturing information about the system and the environment that a particular pipeline is running in. So that's why we think they're more complementary than in conflict. So I tend to think of it kind of like collecting a SLSA provenance document and an SBOM for any sort of software artifact. So yeah. I think you had a question before, Manila. Yeah. Which page? Okay, sure.
I'm not sure. What is the difference between applying all processes to CTPA or
So let me actually go over here because I think I put transparency log in here, but SigStore would be that transparency log, for example. And so are you familiar with SigStore? Somewhat? Okay. So SigStore tracks generally signed metadata of any sort. And so the idea here is that we generate CTPA formatted metadata, and use SigStore to actually track as that metadata is being issued. And so again, it's sort of a complement of the two rather than them being different, sort of conflicting technologies. Does that answer your question? Yeah. Okay, please go ahead.
I remember that CTPA this morning, the keynote, and the person who was talking at the time talked about how a user might expect to someday see a little watermark figured out around it to let them know as an end user that this is trusted from some source.
Yeah.
So the question that you talked about with the stack, is it reasonable to think that at inference time, the output of an LLM could somehow be marked with this metadata so that the end user could understand?
Yeah, I think that is sort of the pipe dream, is to say, like, we want to get to a point where people don't have to look at JSON files or anything else, but yeah, rather just see the kind of nice little check mark that we want to see. Yeah.
And somehow verifiable.
Yeah. So, yeah. The user would have to find a sort of a link back to the information, right? And yeah. Any other questions? Okay. If not, thank you again so much for coming. I guess I give you 9 minutes back before your lunch. And yeah, have a great rest of the week.